Hi, this tutorial on aldehydes and ketones and their reactions with potassium cyanide is the last little bit of your aldehydes and ketones topic. So previously you've looked at the reduction of aldehydes and ketones using sodium tetrahydridoborate, and you've seen the mechanism for that, the nucleophilic addition mechanism, where you would see attack at this carbon of the carbonyl group, these electrons here moving up onto the oxygen, and then the oxygen, which has now become negative, attacking a hydrogen and producing the alcohol. So the reaction that we're going to look at now with potassium cyanide is exactly the same nucleophilic addition mechanism. Okay, so before we start discussing the actual mechanism for this reaction, it's really important that you understand what a cyanide ion looks like. So this is the cyanide ion. So it consists of a carbon, which is triply bonded to a nitrogen atom, and the carbon, only making 3 bonds rather than 4, has a lone pair of electrons sitting on it, and it has a negative charge. So here's an example of a compound containing cyanide. This is hydrogen cyanide, and in water this can split into H+ ions and Cn- ions. It actually doesn't do it to a great extent, which is why it's a bit of a problem using hydrogen cyanide for this particular reaction. Was one of the problems, but you can see that if the hydrogen was to leave, the electrons would move from the bond onto the carbon atom, leaving you with an H+ ion and a Cn- ion, and the electrons that were in that bond there have now moved to here as a lone pair on the carbon atom. So this is our nucleophile for this reaction. Now, to an extent, hydrogen cyanide does work for this reaction. It just doesn't work particularly well, partly because this doesn't happen very much. So hydrogen cyanide tends to stick together a little bit more as hydrogen cyanide and doesn't release too many cyanide ions, which is what you actually need to get this reaction with aldehydes and ketones to go. So instead we use something like potassium cyanide. So potassium cyanide does split a lot more, so you do end up with a much greater concentration of free cyanide ions in your solution. Okay, so this is our nucleophile, so let's put it with an aldehyde or a ketone and show you what happens. Okay, so here we have got an aldehyde, propanol. I've put on the partial charges, so the polarity in this bond gives the oxygen a partial negative charge, so I've labelled it delta minus, and that leaves the carbon a little bit electron deficient, so I've labelled it delta plus. Then we've got our cyanide ion, drawn very carefully to show that we have got a lone pair on the carbon and that the negative charge is also on the carbon. There is a lone pair on the nitrogen as well, but you need to be careful because the bit that attacks the negative charge is actually on the carbon, so that's where attack starts. Okay, so in exactly the same way as your reduction reactions with your sodium tetrahydridoborate, you have the nucleophile attacking the delta positive carbon atom, and those incoming electrons repel electrons in these double bonds up onto the oxygen atom. That's the first step. Okay, so here we've seen a bond formed between the carbon of the cyanide ion and the carbon of the carbonyl group, so that bond has been formed here, and here a bond has been broken as electrons have moved up onto oxygen, so we've now only got a single bond, and the electrons that are now up on this oxygen show as a lone pair and a negative charge. So this is our intermediate. So the next step would be that this oxygen, just as in the previous example with the sodium tetrahydridoborate, would pick up a hydrogen from the solution. So the lone pair of electrons attacks an H+ ion, and that is a bond formed there as well. Okay, just realised that I'd missed a few hydrogens out here, but I've drawn them in now. So this is the product. So the electrons from the double bonded oxygen moved up onto here, and those electrons then attacked the hydrogen, giving you a hydroxyl group, and the cyanide ion attacked the carbon and has formed a bond there, so you've got the cyanide group added in. So this is known as hydroxynitrile. So the nitrile part, that functional group there, takes a suffix, giving the alcohol group the prefix hydroxy. So this is a really useful reaction because it allows you to add more carbons into your carbon chain. So initially, where we've started off with 3 carbons in a row, we've started with a prop chain. Now you have to be very careful because actually your longest carbon chain has an extra carbon in it, and it's now a bute chain. So the name for this product is going to be based on butane, so it's butane nitrile. And you need to take care because it does actually have the full alkane naming, including this A and then nitrile, so butane nitrile. And attached to the butane nitrile, we have got a hydroxy group. So your nitrile is the most important, that's going to take carbon number 1. So this must be carbon number 2. So in your hydroxy nitriles, always number your nitrile carbon as carbon number 1 and number your chain that way. So this is on carbon number 2. So the full name for your product is 2-hydroxybutane nitrile, and you need to be able to draw these, you need to be able to name these, obviously you need to be able to outline the mechanism. So hopefully you can see that that's pretty much exactly the same as the mechanism for the reduction reactions, taking them back to alcohols, just you're adding in the cyanide, and the ketones do exactly the same reaction, so I'll show you an example with a ketone as well. Okay, so this time we're going to start with propanone and the cyanide ion. So first of all, we're going to put on partial charges so that we know where the attack's going to take place. So the oxygen, being more electronegative, is partially negative, and the carbon with the electrons withdrawn from it is now partially positive. So you've got clear route of attack for your cyanide ion. So from your lone pair, your curly arrow is going to attack the delta positive carbon. In exactly the same way as before, electrons are then going to be repelled from the double bond onto the oxygen atom, and that will form an intermediate with an oxygen with a negative charge. Okay, so there's our intermediate, and the next thing that happens is the lone pair on the oxygen then attacks an H+ from the solution to create the hydroxy group. So that gives your final product, this hydroxynitrile here. So this time you can see that you've still added another carbon in, so this is the carbon that you've added in, but because you've started with a ketone, you've actually still got the same length carbon chain here, because whichever way you go, you've got 3 carbons, and you want to include this in your main carbon chain. So you're still going to name this based on prop. So you start with propanone, this is going to be a propane nitrile. Okay, then we need to have a look at what's attached to it. So obviously you've got your hydroxy, and your hydroxy group is on carbon number 1, 2, carbon 2. So it's going to be 2-hydroxy. But you've also got, if we consider that our compound goes this way, you've also got a methyl group as well, and this is also coming off carbon number 2. So you've got 2-hydroxy and 2-methyl coming off of that propane nitrile backbone. So putting those in alphabetical order, your full name for your product will be 2-hydroxy 2-methyl propane nitrile, and we are considering this to be our longest carbon chain. That means that this is listed as a prefix and this is listed as a prefix, and the suffix is given to the nitrile group. Okay, and that is basically it for the nucleophilic addition reaction. So obviously you need to be able to name the mechanism, so I'll write that down for you. So this is a nucleophilic addition reaction with a cyanide ion behaving as a nucleophile, and it gets added in to the aldehyde or the ketone. Now, this reaction can give you some products that can exhibit stereoisomerism, can exhibit optical isomerism, so I'll show you an example of that now. Okay, so here I've drawn out 2 different reaction mechanisms. It's exactly the same thing that's going on. We've got nucleophilic addition of cyanide, but the top one we've got an aldehyde, and the bottom one we have got an unsymmetrical ketone. So if you look at where your carbonyl is, unsymmetrical just means that the chains either side are not the same. So we've got a methyl coming off this side and an ethyl coming off that side, so that would make it unsymmetrical ketone. So I've drawn out the full mechanism just so you can see, but you should be able to do this now anyway. So cyanide attacks, electrons move up onto oxygen. That lone pair of electrons attacks an H+, produces a hydroxyl group. So this is your product, and if you look at it, the product that you've just formed now has a carbon atom that is attached to 4 different groups. So in this direction we've got a methyl group, in this direction we've got an alcohol group, this way we've got hydrogen, and this way we've got the cyanide or the nitrile group. So 4 different groups attached. This carbon is chiral. It will exist as a pair of optical isomers or enantiomers. Likewise on the bottom we've got the cyanide attacking, the electrons moving up, the lone pair on the oxygen attacking a hydrogen, giving you the hydroxyl group. And if you look closely at this compound, you will see that the carbon here is also attached to 4 different groups. So this carbon is also chiral. So in this direction, we have got a methyl group. In this direction, we've got the nitrile group. Here we've got an ethyl group. And here we've got an alcohol group. So, carrying out this reaction will result in enantiomers, and importantly, it will result in a racemic mixture of enantiomers. So any aldehyde at all that you start with, or any unsymmetrical ketone, will give you a racemic mixture in your products. The only ones that won't is if you start with a symmetrical ketone, because you'll already have 2 of the same group attached to the carbon that would become chiral otherwise. So you need to be aware of it, and you need to explain why it produces a racemic mixture of enantiomers, and it is to do with this area of the compound here. So this trigonal area here is in fact trigonal planar, it is flat. Likewise, this bit here is also flat. So if I try and draw this on the side, okay, so if you can picture this as being the carbon of your carbonyl, so if we look at this area here, this carbon is this one here. It is double bonded to an oxygen pointing back into the screen, and it is single bonded to a hydrogen pointing towards you. So this is completely flat in this direction, which means that when your cyanide comes in, you can either get a tack from the bottom onto this delta positive carbon, or you can get a tack from the top onto that delta positive carbon, and they happen with equal probability, completely equally likely that cyanide will attack from the bottom and from the top, because this area of the compound is completely flat, it is planar. So the key word you'll want to put in your answer if you're asked about why these reactions will produce a racemic mixture. The carbonyl region is planar, completely flat. Equal likelihood of attack from the top and from the bottom. And that will result in a racemic mixture. Okay, so you can imagine that where they're currently flat, as this cyanide joins on here, this carbon will become tetrahedral, so this will shift up, and that will shift up, and the cyanide will stick at the bottom, or the cyanide will join the top, it will form a bond here, and that carbon will shift down, the hydrogen will shift down, and the oxygen will shift down to give you a tetrahedral shape there. So they are non-superimposable mirror images of each other, and they happen with exactly the same probability, so you'll get a 50-50 mixture of both. So that is all for aldehydes and ketones. So you need to know about the reduction and oxidation between aldehydes and ketones and the alcohols and the carboxylic acids. You need to be able to write about and draw the mechanism for the reduction using sodium tetrahydroborate, and you also need to know about and be able to outline a mechanism for the nucleophilic addition reaction with potassium cyanide. Just a brief mention before we finish, potassium cyanide is used rather than hydrogen cyanide, partially because of what I said at the start, where the hydrogen cyanide doesn't split up enough, but also because hydrogen cyanide and potassium cyanide are very, very toxic. But hydrogen cyanide's a gas, potassium cyanide is a solid, a little bit easier to work with. But it is worth knowing that your potassium cyanide, it does give off vapours, small amounts of vapour of hydrogen cyanide as well. So neither of them are completely safe, but potassium cyanide's easier to work with and is a little bit safer to handle than hydrogen cyanide. So if you can check that you've got your tutorial notes and complete your post-tutorial quiz for Monday, that would be great.